Okay, so again, thank you very much for the invitation. It's very I think I really like to share what I know, and I really like to see students here because they are our future, basically. So so Aina has asked me to share something about the application of heat integration and then how we can apply it in our typically in design project for undergraduate, also for masters for PhD. So it's for the design project. So what to do and how to do it, and then basically yeah, how to make sense of that. Before going to that, I have some disclaimers. So, because we only have like a 2 hours, and then I need to say so that this is not a complete detailed course on heat integration. Yeah, this is not. So I will skip some topics, um, and then these two is more like this heat integration or pinch analysis as we know it. This is merely like a methodology. So this methodology is a straightforward methodology, and it demands, because this is a methodology. Yeah, it's not something very special or something. So it demands our knowledge on the process that we're dealing with, and also the process engineering skills of the team members. In practice, this work is a teamwork, and then in the team of this kind of project, there should be a person who is like an expert or know a lot about or have applied these pinch analysis concepts into practice. So we need to have one person like that, and then we need to have people in the process engineering, and then the design team, and also the mechanical, and then the maintenance team or the operational team, because when we come up with some solutions or with some options, the mechanical people and then the operational people, they can have a say whether this is like a viable solutions, or what other things that we need to do or to add to implement such solutions. The outline is that I will share some. I think I will share 3 projects of mine in the past on what kind of heat integration project, integration projects that I've done, and then how to integrate, how to apply this in typical undergraduate design project. So I'll be talking about we need to do some targeting from the base case design. So which means that we have to have a base case design first, and then we do the targeting, means the energy targeting, how much is then the minimum energy that we can achieve from the thermodynamic standpoint. And then is there any process modification that we can do, or can we see that, how can we see that if such modifications that we do, it will reduce the energy consumption. And then lastly, once we know the minimum target or thermodynamic target that we can achieve, and then we have done some modifications, and then we can then go to the heat exchanger, to the designing of the heat exchanger network itself. If you have any questions, just let me know. Yeah, just write it on the chat box. Maybe then I can answer it if I see it, and then you can just simply ask me or interrupt me. So we make it as casual as possible, because I would like to have discussions, because I think the theory you get it already from the schools, and then you can get the theory from these books. So these are the books that I at least these two. These books, this is the well-known book on pinch analysis and process integration. So this is already the second edition. The first edition was written by the inventor or the original people who developed this method, which is Linhoff. And then at that time it was in the University of Manchester, and then this Robin Smith, Robin Smith is in the University of Manchester nowadays. So this is his book on the second edition already, Chemical Process Design and Integration. So I for students, I always say these textbooks is very important. So you have to have it, and then you have to sleep with it. And by the end of your fourth year or master's or whatnot, you have memorized this from cover to cover. That's what I always say. And then from this book, yeah, is there any
soft copy for this?
I think soft copy, yeah. You can I think you can find it online. Yeah, I have, because I have soft copies. I can share it later. I have soft copies which I found online as well. For this book especially, they had like a competition among students who can make a tool for pinch analysis, like a simple tool for pinch analysis. I put it here. I think later I will share this slide, and then you can just have the this Excel sheet. But you can Google pinch analysis, and then ICAME pinch analysis ICAME. You can Google it, and then you will get that Excel sheet. I think you can see that later. This is at least one of the tools that I have. I have also my own Excel tool I developed, I think 12 years ago, something 12, 11 years ago. And then I also have this, and I also have another Excel file from another company. For software, we have the Aspen Energy Analyzer, which we can use. We can also have the it's come from KBC Super Target software. So this Super Target was like a spin-off of I think, yeah, it was a spin-off of a company from University of Manchester and from Linhof-March, I think, as well. So they bought Linhof-March was bought by KBC, and then Super Target is one of the software that they bought. So this Super Target is also a tool. I think it's much better than the Aspen Energy Analyzer, but everybody has this nowadays. And also, if you Google, I think if you Google HINT, 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 heat integration, heat integration, you can Google that, and then you can get the education version of heat integration software. This was like an educational software, so nobody maintains this software, but it is good enough. It is good enough for teaching and for some simple application. So heat integration in practices. This was my recent project. So that we have a refinery in Malaysia, and we have like CDU, crude distillation unit, and also the CFU, condensate fractionation unit. So this CDU and CFU, they are connected by one stream. And then typically we have from the tank, the crude oil is then pumped through a series of heat exchangers. It's pumped. I don't know, maybe it's pumped from here. It could fit. It's pumped from here, and then it goes through a series of heat exchangers, and then it goes to furnace, and then it goes to the CDU. The same goes with the CFU. We have the condensate feed, and then it goes to a series of heat exchangers, and it goes to the CFU. And then the question is then, what can we do? Can we increase the heat recovery? Can we minimize the heat consumption in the furnaces? So that was the questions. So what we did at the time is that we gather the data, and then we make our simulations to calculate the mass balance, because to do this this kind of study, we need to have the mass balance correct. And then from this mass balance, we need to know the flow rate, basically. We need to know the heat capacity, the enthalpy, and then we also need to know the inlet and outlet temperature, the supply and demand required temperature of each stream. And then we have two cases. We have the light cases, different crude, yeah, light crude, and then the heavy crude cases, and then we have the design case. So when we compare the energy consumptions, we can see the design case is 87 megawatts. A light case is slightly higher, and then is higher, and then heavy case is just slightly higher. So can we even decrease it even more? So that's what we did. So we make the graph and stuff, and then we have this grid diagram for all of the exchanges, and then you can see, for example, yeah, the red ones are heaters, the furnaces. These are the ones that we want to reduce its duty. The blue ones are coolers, air coolers or condenser. And then this exchanger like this, if it has like a one line and then two circles, we typically say this as process-to-process heat exchangers. So we want to maximize the energy usage in all of these process-to-process heat exchangers in such a way that duty being imported in this furnace is going to be minimized, and also duty removed in these blue lines, blue circles are also minimized. So this was the latest one, and then this one in the Netherlands, the one that I did, I was involved in back in 2011, 2012, 11, 12. So we have a chemical plant, which with this, so we have some series of heat exchangers, some reactors, and then two distillation columns. And we take the data, the operational data, and then I made I think you guys all know this, what we call like composite curve. So we have the hot composite curve, we have the blue composite curve, sorry, the cold composite curve, and then the overlapping area is then the area where the recovery can take place. The non-operating area, for example, in this area, this is then the minimum heating utility that we require thermodynamically, and it's also minimum utility that we have to discharge to the environment. We send it to cooling tower. And then the same with the grid diagram, and then we found out that we could then we add one more heat exchanger over here. If you can see, so there's one heat exchanger over there, but now we add another one to recover more heat. So we make a branch, and then recover the heat over there, and send it back to its own route. And then the other one is this is like 1 year older than the previous one, so this is then the oldest project of heat integration that I've been involved in. So we have a plant in China. These are the same system. We have this is then the high pressure users, low, medium pressure users, and then the low pressure users. Make this grand composite curve, and then we can see that there are. We can see that there is this horizontal line. I think we understand that this horizontal line symbolizes the latent heat. Yeah. So this latent heat typically comes in the reboilers or condensers, but in this case it's reboilers because it needs heat. So because it needs heat, it means it is on the reboiler side. And then we look into this, and then we saw that this is one of the big columns, and then that big columns, we can reduce the pressure of that column in such a way that the temperature level will then change. It will then drop somewhere here below pinch. So that means we can then remove this whole duty and then create another duty over here that is being released to the environment. So that's what we do. So we change one of the exchanger there, the pressure, we change it to the lower pressure, and then the excess steam we send it to a nearby plant. So that's what we did. So these are the three cases that I've involved in. We can talk about this in a little bit more detail later on if you want. You can ask me. But now go back to the main topic that we are why we are here. How to apply this basically. So I've shown you how to what I've done in the practice, and then which I touch a little bit on how I did that. Yeah. And then where I showed you the composite curve and then the grand composite curve. So these two curves are very important to see the targets, yeah, how much thermodynamically that we need from the utility for heating, and then how much that we have to destroy in the utility for cooling tower, for example. And then from the grand composite curve, the idea is then to see what are the correct placement of utilities. So what is then the required steam pressure on the field? Are we doing it okay, or can we then change the steam pressure? So those things we can answer by having this grand composite curve, and then lastly by having this grid diagram, we can see whether some of the exchanges, whether they are violating some of the rules, and then we can then make corrections based on that. So these three things, I repeat, the composite curve is very important, and then the grand composite curve to see the utility, and then the grid diagram is then to evaluate and then also to modify how to design the heat exchanger network, basically. All of this we can do it in software, but then without knowing the basis, I think it's going to be very difficult to really put that software into its useful or its full potential. Yeah, so we have to understand the basic, why we do so, how we do so manually. That's why we have this heat integration course. Then we can on practice we can simply use software. I'll start with the with this, for example. Yeah, assuming that you have like a flow sheet. Because in your design project, you design the process. Typically, we design the process in the class. We design the process using this onion diagram from Douglas. So we start from the reaction, and then that reaction design we use it to design the reactor. Yeah, we know the kinetics, and then from the kinetics we design how big is the reactor, how much is the conversion that we allow, and then what is then the selectivity, and then in the end, what is then the what are the unreacted raw materials, and then how much is then the byproducts. All of those we use them to design the separation and recycle system. And then once we design the separation and recycle system, I'm not going into details on this. We'll just guide you through it here. And then once we know what to separate, what to recycle, we will then end up with this kind of flow sheet basically. So we have for example, this is just an example. So we have a feed coming, and then it has this heating duty. For example, it needs to be heated like 240 kilowatts, right, from 80 degrees C. Somehow, and then it goes to the reactor at 140 degrees C, and then we have 2 reactors in series, and then it is to be cooled down, and then it goes to the distillation column. We have a condenser, and then we have reboiler, and then we have somehow we have a product over here. So we basically need to know, we know this needs to be heated, that needs to be cooled down, this needs to be heated as well, this needs to be cooled down. So we know this basically. In a way that I'll just use pen. I like using pen. In a way that using this information, where's my pen? It doesn't work. No. So we know that this is then the this is then the stream that it needs to be heated. This is then the other stream that needs to be heated as well. This is the stream that needs to be cooled down. This is the stream that needs to be cooled down. Basically, how do we know that? Because we see the temperature. So we want to know, we want to have it from 80 degrees C to 140 degrees C, for example, and then that means it needs to be heated. That means it is a cold stream, cold stream, because it needs to be heated. And then we have also another stream. It's from 170 degrees C. It needs to be cooled down to 60 degrees C. That means because we need to cool it down. So this stream is then the hot stream. This one as well, it needs to be cooled down from 150 degrees C to 30 degrees C. It needs to be cooled down. That means this is done a hot stream. The last stream, it needs to be heated up from 20 degrees C to 135 degrees C. That means these streams are. Stream is then the cold stream basically. So up until this point, up until here in the second layer, we know already what to be heated and then what needs to be cooled down. And this information is necessary to go to the next step, which is then the heat recovery system, which is then going to be used for heating and cooling utilities. So these two layers, they are very much related to each other. So pinch analysis, in this sense, pinch analysis is that it is a tool or methodology to set a target. So if we have a flow sheet like this, the question is then, well, we can design, we can design the heat exchanger network, whatever we want. But then the question is then, how do we know whether what we do is better or best? Yeah. So best here means it will then satisfy this thermodynamic constraints. It has the minimum total cost, for example, or it has the maximum profit. And then because there are so many designs that can be done, we can then know whether one design is better than the other. So this pinch analysis is kind of like it sets the energy target based on thermodynamics. Without us doing anything, without doing any design, we know already beforehand, without doing any design, we know already beforehand how much then the energy that we require for heating, and then how much energy that we have to discharge for cooling it. Yeah, so that's basically the main message of this pinch analysis tool. Yeah, without any design, without doing any design, we know already what is then the target, the goal that we can achieve theoretically. The step is, as we know already, so we've discussed briefly, identify the hot and cold streams, which we have done. So hot stream means if it needs to be heated, it needs to be cooled down, sorry. Hot stream means if the stream needs to be cooled down, that means it's a hot stream. And if the stream needs to be heated up, that means it's a cold stream. So we take down the flow, the heat capacity, and then the inlet and outlet temperature, or supply and demand temperature, or supply and required temperature, whatever you want to call it. And then we select delta T min, and I will show you what this delta T min means. And then based on this delta T min, we then construct the composite curve and then the grand composite curve. And then we can then see the minimum energy target. So this is then the first thing that we can see. We don't have any design, it's just constructing, getting the data, and construct the curves, and then we get the energy targets. And then we could also do, is there any, from these energy targets, we can ask ourselves, we can go back to the flow sheet. We can ask ourselves, can we do more? Can we reduce the energy targets, or can we do something else? So this is then the things, the techniques that we can do. I will show you in a minute. And then we can also do some integration of process equipment, among other things, within this process modification realm. And then after that, we can then do the estimation of heat exchanger network. I think for this topic, I will skip, for this short talk, I will skip this. But nonetheless, I can give you a hint. And then we can then say, okay, so for this specific, for example, for in one delta T, we can have one delta T of what is then the design of heat exchanger. Sorry, the cost. The cost. And then we can then check another delta T, for example, delta T2. Delta T2 over here, and then from this delta T2 we can also have another delta T2 cost, the cost associated with this the second delta T min, for example. And then once we are satisfied with the minimum delta T min that we select, and then we can go to the design of heat exchanger network. So this is basically the formal procedure, which I modify and add a little bit here and there, according to my experience, that we can follow. Do we have to follow exactly how it is? The answer is yes and no. Yes, if I mean it's good, because it's a in the end you will then follow this subconsciously, but then to really follow this, for example, after this, and then we go to that one, and then do we need to do most process modifications? In some cases we cannot do, or we cannot modify process, so we can skip this, we can skip that, we can skip this, and we can skip that as well. So we can go to here. But then do we need to change the delta T minimum? Yes and no. If you want, you can, but if you don't want to do that, you can just go straight to the design. So that's basically the things that you can. The more you have, the more experience that you have on this, the more you can have a feeling on which steps that we can skip, and then to make it much more realistic. This I always put it on the screen because in this work, especially in this work, for this heat integration, we only need to memorize 3 equations, which I think you have memorized this by heart. So the first equation is then QMCP delta T. Everybody knows this. And then we have for example, we have a hot stream. And then we have a cold streams. Cold streams again needs to be heated up. Hot streams needs to be cooled down. And then the Q or heat, it can only be transferred from high temperature region to the low temperature region. It's not the other way around. It's not from low to high. It's from high to low temperature region. So that's by nature. That's what we call sunatullah. And then the second equation is that we have in a heat exchanger, for example, we have cold streams, we have hot streams, and then the amount of Q we can then determine once we know, for example, we have the data in the feed, we have the data in the outlet, we can simply calculate how much is done in the Q. And this Q or the heat needs to be transferred via a heat exchanger. So this heat exchanger, we can then calculate what is then the size of the exchanger, and then by assuming a certain overall heat transfer coefficient, which we can check later on. So that comes to the second equation, which is the transfer, the heat transfer equations, which is Q equals to UA delta T LMTD. And this delta T LMTD makes the last equation, which is simply the delta T over here minus delta T over there divided by the ln delta T here divided by delta T over there. So that's basically this delta T LMTD. So you don't have to memorize. You don't have to memorize all of this stuff. It's just delta T and delta T. Minus them and then divided them in logarithmic and natural logarithmic. Come back to the our small example. We have once we know the flow. This flow is MCP. It's not only the kilogram per second or kilogram or mass, but in this case it is MCP. So kilogram per second multiplied by kilojoule per kilogram degree C. So that's why we get this kilowatt per degree C unit. This MCP is very important, and then we know what is then the supply temperature, we know what is then the required temperature, and then from these three items we then calculate the load. Or if we don't know we could also say I know the temperature in and out, but then I know also the load, and then from these three numbers I can then calculate for me the MCP or the flow. So that's basically these are the table, the important data that we need to have. Without this data, we cannot move forward. Yeah. So what happens typically in the class or in universities, in schools, we have this data. Yeah, in schools we have this data, but in practice, well, we have to fight our life for this. Yeah. Sometimes the temperature here, thermocouple over here doesn't work. Sometimes this one doesn't work. Sometimes we don't have any thermocouple, and then sometimes there is no measurements on the flow. There's so many dramas, basically. So so what we do in that sense, we make a process flow sheet. We make the simulation model to calculate the missing information, and then use that missing information to use that calculated numbers and put them into this table. So from this data, there's also like data extraction rules, but I think I can skip this. I can skip this. You can read this later, or you can ask me during the Q&A if you want. From that data, we can then generate what we call like a cold composite curve, and also the hot composite curve. Yeah, cold composite curve are the cold streams smooched together, and then the hot composite curves also the hot streams combined together. Just quickly, I think I'm sure that you know this already, but just quickly, and then I don't think you need to do this as well manually, except in your exam or in your homework. But then we have two hot streams, yeah, like in this case, we have two hot streams, right? Two hot streams, and then two cold streams. They have one cold streams, and then this also cold streams, and then we have hot streams over here and then hot streams over there. So two each, and then for the hot stream, the same with the cold streams. We have the enthalpy on the x-axis, and then the temperature on the y-axis. We can then map it. For example, this stream number 2 and number 4. So stream number 2, it starts from 170 and it ends at 60. You can see here. So stream number 2, it starts from 170, ends at 60, and it has this MCP of 3. Yeah, 170, 60, and 3. So when you go here, so we have 170. It starts from 170. It ends at 60, and then the CP is 3. So this CP or MCP is basically because we have this temperature, we have this enthalpy, and then we know that Q equals to MCP delta T, right? And then we know that delta T is on the y-axis, so if we then put delta T divided by Q, it's going to be equal to 1 over MCP, right? So this 1 over MCP is then the slope, the slope of the curve. And then we know if the MCP is high, if the MCP is high, that means the overall stuff here will become lower. So if we have a bigger strip, for example, a big strip, huge M, that makes the MCP is then high. That means the slope will become shallower. So that means if we have CP equals to 3, so if we have CP equals to 10, for example, it will become shallower like this. So then, for example, just to pick a number, and then if the CP is then lower than 3, that means the MCP is then becomes lower, and then that makes the 1 divided by something low is something big. So that means it will become something like this. So this is made for example MCP equals to 2. So from here we know which streams are basically very sensitive to temperature. Yeah, if the MCP value is very small, it means they are sensitive to the temperature or to the load. If the MCP is big, that means it's not very sensitive to the change in temperature, or the heat load is that we give to them, it's not enough, or it's only able to change the temperature slightly, just like in this case. Yeah, we have like, for example, we have given them this amount of half of megawatts of energy, but the temperature only increased from 60 to 150, for example. And then we divide this. So once we know the streams, in this case we have 2 streams, we divide them into intervals, according to their intervals. So we have 1 interval, 2 interval, 3 interval, and then for each of these interval we just simply sum them. So this part, I'll give a different in color. So this part is here, and then this part is over there, and then this 2 stream and that stream, we sum them, and that makes this. So we sum them. For example, this is 1.5, and this is then 3. So 1.5 plus 3, it's a 4.5, and then that's 4.5 is this line. You can do this mathematically on your own. So since we use software, so we don't have to deal with this detail anymore. And then so if we have like tens or dozens of streams, so we're not going to do this manually. So we'll use software, and this is what we come up with. In the end, we have the hot composite curve, hot composite curve, and then we have the cold composite curve underneath, and then the area. So we can see this area. So all of these are the area where heat recovery can happen, and then this part is then the this part is then the external utility, like furnace or boilers or whatnot, and then this also from here to there roughly, it's also going to external, like cooling tower and stuff. So this is what we call like a minimum cooling utility, which happens to be 105, and this is then the minimum heating utility of 65. And then the area where they touch each other, I will then change it to the area where they are the closest to each other. This graph, the points where they're closest to each other is this point, for example. So this then the points. So the hot pinch temperature is 100. We can see this 100, and then the cold pinch temperature is 80, and then in between it's a 90. So this pinch temp, this is what we call the 90 is then what we call pinch temperature, and then delta T is 20 degrees C. 20 degrees C. And then obviously we can then increase this delta T, or we can change the delta T. How can we change that? It's not by increasing the hot stream up, or the cold stream down. It's not by doing so, because this whole temperature is fixed by the process. We don't change the temperature. So what we change is then we just move it to the right or to the left. This blue line, basically this blue line. We move it to the right or to the left. So say for example, we move it. If we move it to the right, that means this blue line will then become something like this. And then obviously the delta T between them getting bigger, right? For example, this is then the delta T. So this delta T is then bigger, but then you can see the distance. See, this is going to be larger, right? This is E2, for example. So this is E1. So this E2 is larger than E1. So that means the if we put it to the right, that means we will have we will need more heating utility. The same goes with this cold utility. We need to discharge a larger heat to the environment, and then the area where we then do the heat recovery will become smaller. Same goes if I then need to be purple maybe. So if I put to the left, yeah, for example, and this becomes something like I don't know, something like this. So yeah. So now in this case, for example, I have no, there is no heating utility required, but then I only need to discharge this amount of energy to the environment. But in this case, I can also recover huge amount of energy in the process. But as we can tell, yeah, it comes with a penalty. This purple, we know that the delta T, so delta T is then smaller than the blue one. Blue, yeah, blue one, delta T blue, and this is also smaller than the delta T red, right? You follow me, yeah? So this red is over here, this red delta T. Is the blue one, is then the purple one. So delta T is then smaller and smaller. Means the heat recovery is getting bigger and bigger. Yeah, the utility, the external heat is then getting bigger. If we go from here to there, this is then the heating requirement. The heating discharge to the environment is getting sorry, the this is not the other way around. So the external utility becomes smaller. We go from here to there, but then the heat recovery is also becomes bigger from here to there. Yeah. So the amount that heat that we're gonna cover from here, for example, this blue line until that one, it's bigger than if we start from here and there, or from here and here. But this comes with a penalty, as I said, because we have a smaller delta T here. So it seems to be tempting, right? It seems to be tempting if we then reduce delta T as much as possible. We will then have a lot more heat import that we have to get from the external. We can recover heat as much as possible, but then because we have a smaller delta T, you know that the Q is then also UA delta T LMTD. So that delta T is then correlated to that delta T. So the smaller the delta T, the smaller that one. So to recover the same amount of energy, we will have to have a huge amount much larger area of the exchanger. So it means larger heat exchanger. So see if you have some space on the field. If you don't, and then we are limited to that space. So this is what I've been talking. So we have the different scenarios for different delta T, and it's also different scenarios for different ones, yeah, basically. So in some cases we have the external cold utility, but we don't have any hot. So in other case they have hot utility but no cold, and then we have also we have cold utility here, and also cold utility over there. So we have high and then low cold utilities. There's no hot utility. We could also see the situations where we need to have hot utility in both sides, the lower and then the higher and then the lower. And then we could also have like a multiple pinch points, for example. So we have a pinch point over here, we have a pinch point over there. So anything can happen, yeah. Anything can happen. It's just that we need to know, what our system looks like, and then what we can, what is the consequence on that. So after this, do you have any questions? Is there any questions or no? If not, then I can continue.
Yeah. Usually, when you guys decide to find a pinch,
Sorry.
when did you consider to apply this pinch? Is it during the development or during the operations?
This one, okay, go on.
And then, is there any range for delta T?
Yeah, Good. With all of this, we apply this work in both in design and also in during the debottlenecking. Yeah, means design in the like a green like a design a sketch, or design during the retrofit or debottlenecking. So we can see what is then the impact of our delta T selections to how much energy that we can recover, and then how much investment that we have to account for. For example, in this case, we can then see how much energy that we can recover in this, and then we can also see simultaneously we can see, or we need to see, how much investments that we are talking about. We can pair on. But then the next question is then more interesting. So do we have kind of guidelines on this delta T? There is a guideline. But again, this guideline is only a guideline. It will be different from plant to plant, how old is the plant, and then what kind of modifications have been done, and then what is then the current situations of the plant. So all these things and where we are on this globe is also important feature in selecting this delta T. These guidelines, we can find it in the, I think we can find it somewhere in the, I'm not really sure, yeah, but I think we can find it in this book. Otherwise, we can just simply Google. I think there's this IEA, because I don't remember. I've seen this table somewhere. We can see IEA Energy Primer. This written by people from northern Scandinavia, from Denmark or Norwegia. I don't remember. So in one of these articles, I think they know. They make this table on what is then the typical numbers. So if I can remember that correctly, for petrochemicals, for oil and gas, we typically use this 20 degrees C or 30 degrees C simply because it is strongly related, as we see already. It is strongly related to the trade-off between how much energy that we can recover and how much investments that we have to pay for that. Yeah. So in typical refining and petrochemicals industries, we can go by 20 degrees C or 30 degrees C, the delta T. But for refrigeration, for example, we can go even to as low as 2 degrees C. 2 degrees C, because in the refrigeration, we know it is sub-ambient. Yeah, we have ambient conditions, and then this refrigeration is below zero, it's sub-zero. So the more we go down in temperature, the more energy that we need to run the compressor, and then the bigger the compressor itself. So that equipment is very expensive. So to cater for that expensive, I mean, we can then because we need to be able to recover heat as much as possible. We need to be recover heat as much as possible because of that expensiveness. So hence we can then comparing the cost of the compressors, we can pay more heat exchanger instead of more or bigger compressors from that perspective, from that refrigerations. Hence they tend to use much lower delta T, like 2 or 3 degrees C. So it really depends on the plant and then where we are also in the business, depending on, for example, the heat utility. Is this cheap or expensive? If it's cheap, and then I don't care. But then if this is expensive, and then we have to be worried. So if the steam is expensive, for example, if the natural gas is expensive as a source of the heating, if they are expensive, that means we better recover as much as possible. We will better recover as much as possible. That means we will have to reduce the delta T as much as possible. We have to pay more on the capital investment. But if the heating utilities is not expensive, so it's just simply cheap, so that means we can be relaxed. And then we can then design a small heat exchangers to recover process-to-process energy. So that's basically what we typically do. Okay, I'm halfway. Now, You can this one, yeah. So now I'm messy, but at least you can see the curve, they don't touch, yeah, they don't touch, and then we see the delta t is 20 degrees C. But to make the grand composite curve, we have to adjust the temperature. To make the grand composite curve, we have to adjust the temperature. How do we do so? We drop the hot curve by half of delta t. Yeah, so that means the delta t is 20 degrees C. So half of that is 10 degrees C. That means we go back to here, we go back to there. So the hot curve, we drop it by half here, obviously. So this is going to be 160. This is going to be like a 50. So the same goes with here, it's a 140, and this is then 20 degrees C. The same goes with the cold. So the cold composite curve, we increase it by half. So in that sense, we change this table into 30, and then this then 145, this then 90, and then this then 150. Change the temperature. The rest is the same, yeah. And then we get this curve, and then this curve they touch. And this is then the beginning of that pinch name. So they pinch at this point, which is 90 degrees C, 90 degrees C, and then we can get this graph. So from this adjusted temperature, we can then make the grand composite curve. I'm not going to explain how we make this, but then you can go back to the textbook. So from this, we can also see the same thing, yeah, minimum heating utility of 65, and then make minimum cooling utility of 105 kilowatt, which is 65 is coming from here to there. So you can see 65, and then from here to there, you can see it's 105. What is then so special about this grand composite curve? Well, it gives us plenty of options for utility design. For example, number one, I put everything here, so I hope it's clear. But anyway, so we can supply this at the steam of 170 degrees C. Yeah, when we put it into this grand composite curve, obviously we need to drop this by half of the delta T. Means from 170 drops to minus 10, means 160. So we can then have a steam over here. Yeah, and then we could also use like a chilled water from 5 to 15 degrees C, all the way 105 kilowatts. So that is one option. The second option could be for example this one. We use the same steam, the same temperature of the steam. Okay, so I did not copy this correctly. Okay, so this is not a good example because this is the same. This one, the second options. So we have instead of steam at 170 degrees C, because what needs to be heated is only this part, right? What needs to be heated is only this part. So in that sense, I can save some energy by using steam of 150 degrees C. Right? So it's 200 degrees C. Sorry, it's 220 degrees C lower. So it could, yeah, in some sense, it could save some energy required to make this steam. And then I can use it, yeah, instead of 170. So that's the second option. And it's also from here, instead of using chilled water all the way 100 kilo 5, I can have this chilled water here, and then the cooling water from this to there. So that's another option. And then the third option is that yeah, I can also use steam at 150 degrees C, and then use another steam at 120 degrees C, right? So two different level of steams. So this could be, so this one could be cheaper. This one could be cheaper than the other one. Yeah, it could be. So if you have these cheaper options, try to maximize the cheaper options. Try to make use of the cheaper options as much as possible, and then we go for the more expensive options. The same goes with the cold utility. Yeah, so we can have the chilled water over here, and then cooling water over there, and then this one, well, you can use it to make a hot water, and then you can then have a hot shower. I don't know. Just use which can be used for other purposes, right? So there are plenty of options to design the utility system simply by looking at this grand composite curve. So that is basically the idea. So once we know all of this, yeah, we know the target. We know the target of the hot utilities. We know the target of the cold utilities. We can then simply design the utilities already. And then, is there anything that we can do? obviously we can then go to the second options. Yeah, once we know the target, we can modify, see if we can do some modifications. For example, so I will tell you now the importance of the pinch point. So these pinch points, we know there is a plus minus principle, they call it. So this is basically the amount of energy that we require externally, yeah, from the steam, from the furnace, from the boiler. Our goal is then to minimize this as much as possible. So we want to contract this, right? We want to minimize this, So how do we do that? We'll then find the process that is responsible to make this to the right. So we have to try to make it as to the left as much as possible, or we need to make it to the right as much as possible. In this case, same goes with here. So this is what we call, this is what they call it plus and minus principle. So we plus this to the right and then we minus it to the left. So it's more like that. Or we can also say, because this stream, yeah, this stream, it takes more heat, so I better than change the pressure in these sections to put it there. So that means I can then add something. I can add something like this, for example. Yeah. So so now I'm moving here to there. So this graph will then go into the left, and then I will have a lower utility for heating, and then I will have also a lower utility for cooling. The same goes with the hot stream. So in this case, we can then simply move this to the above the pinch point. Above the pinch point, we can do heat. You can use heat pump for that. Which we use, yeah, which we use in our, no, we didn't use heat pump, but we reduced the pressure of the distillation column. Remember, in our project in China, we reduced the pressure of one of the distillation column to slightly lower, and it goes below the pinch, and hence this energy is then it's not there anymore. So we can then reduce the heating utility. This is then the pinch and the plus and minus principle. So what we do typically, we change the reactor conversions. We can also change the operating conditions if it permits. Yeah, if it permits. This is what we did. We changed the distillation pressure. We could also change the reflux ratio. We do some pump around. So in CDU, in the cold distillation unit, we have a pump around. The goal is simply to reduce the vapor load, as well as to remove or to recover the heat as much as possible, so that we can reduce the size of the furnace. So we could also use the feed vaporizer. We change the evaporator pressure. We can use heat pumps, like I said. So basically, whatever we need to do to shift hot streams from below to above pinch, yeah. So from here from below to above pinch, we shift it so it can go there. So we can then minimize this. We can then shift cold stream from above pinch to below pinch. Just take it from here, put it over there. Let it goes like that. Yeah. So in the end, we can minimize both the hot and then the cold utility. So that's basically this plus and minus principle. So this really looks into the process. Really looks into the process. What can we do to alter this graphs? So once we do this, yeah, say for example you have done this, yeah, we have changed the distillation pressure, and then this is and then this graph, for example, that graph is then the best that we can come up with. So fine. Now it's time to design the heat recovery part. So this part, design the heat recovery part, as well as this part and that part. There are 3 golden rules to follow. The rest we can do whatever we want, but then these 3 rules we cannot how you call it, we need to obey this as much as possible, because by obeying these 3 rules we will then be able to meet the target that we have specified. Okay. This graph, it's a bit different, yeah. The 105 is there, and then this 15 is because in this exercise in the class that I've done, we did some process modifications, and it comes with instead of 65, it goes to 15 now already. But nonetheless, the concept is the same. No heat transfer across pinch, because means yeah. This is then the pinch point. This is what we call below pinch. This is then what we call area above pinch. Yeah, area below pinch, and then the area above pinch. Okay, so the heat recovery in below pinch, it stays below pinch. So this part, it stays where it is. Yeah, it cannot. We can only use this energy. To hit this stream. Okay, no other stream. And the same goes with this one. this energy will be used as much as possible to hit this stream, yeah, from here. So all of this is needs to be maximized. So we cannot take this stream to hit below here, to hit this guy, for example. We cannot do so. This is not allowed, because if we do so, we are taking this hit from here to down here. That means this guy it's now missing its partner, right? I mean, it needs to be hit by something. So if we remove this part, that means some external utility needs to cover for that. So we are now need to have, instead of only this, we need to have now this plus that, yeah. And then this, and then the on the other side, we have another penalty as well, because this energy is used over here, for example, and then this is going to be utilized over there. But then because we put it over here, and then the existing ones over there, it has to be shifted to the left a little bit. So we may have a curve like this. So we have the same penalty over here. This amount of energy, say this A, is the same A that we took over here, and then the same A that we have to pay there. So we have now, by having this heat transfer across pinch, by A amount, we have to pay two A's. So this is one A, and this is another A. So we have to pay one A in the top as heating requirement, and one A in the bottom as cooling requirement. Yeah, so this is two penalty if we do so. Also, so there is no cooler above pinch, because in this pinch, we only need to have heating utilities. Yeah, only heater is only allowed. So if we have cooler over here, that means we cool it down. So this guy, we cool it down, for example. If we cool it down by heater, that means this guy, which is supposed to be cooling this, it needs to be heated as well, right? Because this needs to be heated. So it will then go over there. So it will then create. So if we say that we put like a B cooler in the top, so we need to have another B over here additionally. Yeah. So it gives one penalty. The same goes if with the heater below pinch, also one penalty with the same logic. By having these three rules, we could also see here. Yeah. These are the three rules. Do not exchange heat across pinch, not use cooler above pinch, not use heater below pinch. And then we start at the most constrained point. When we design this, we start at the most constrained point, which is the pinch point. So these are the rules, but I think you don't need to memorize this rule. I will show you why the rule, why it is what it is in 1 minute. And then also the rest, once we start at the pinch point, and then the rest is then just exchange it as much as possible at the takeoff rule. This also, if you in the textbook, you will see this diagram on how to design below pinch, on how to design above pinch. So you can then follow this strictly. I will show you now. So we start, once we know the streams, we have typically we put it like this. So we have hot streams on the top, and then we have cold streams in the bottom. So it goes from hot stream is then from 180 to all the way to 60. The same goes to 150 to 30, and then this one goes to 135. So we put the stream number, and we have the MCP. We have the MCP next to it. And we know the pinch points, right? We know the pinch points, and then we know the hot pinch, because in this case, if the pinch point is at 90 degrees C, so the hot pinch is then 100, and then the cold pinch is then 80, which is in this case it happens. So this point is 100. This one is also 100. It's also this one is 80. This one is 80. Yeah. So this stream specifically, it starts from 80 to 135. Remember that how to design this, we start at the most constrained point first. Why is that the case? Say, for example, yeah, we have this then above pinch. This is then hot stream, this then cold streams. This part, this pinch, it is fixed, right? This is fixed. So this is then 100. This is 100. this is an 80. This fixed. So so how much can we then allow them to exchange? How much is this? How much is this? So that depends on the MCP over here. MCP, and then this is also MCP. That's why we need to have this MCP next to them, so that we know. Say for example, if the slope is then 1 over MCP, right? The slope is then 1 over MCP, 1 over MCP. That is then the slope. So if the MCP is then too small, yeah, if this MCP is too small, that means 1 divided by something small is something big. So if this guy is too small, that means the slope will become larger. So large that it can then cross this. Yeah? So this is what we call temperature cross. This is not visible thermodynamically. Heat can only be transferred from high temperature to lower temperature. So in this case, yes, we can transfer heat over here, but then above this, it's impossible to be transferred from this stream to that stream. It's impossible. So this is then one of the rules. So if you want to design above pinch at the pinch point, starting from the pinch point, if you want to design it, we have to make sure that this MCP has to be bigger than this MCP. Yeah, this MCP has to be bigger. MCP has to be bigger, because if this is big, it will become shallower than this guy. Yeah, it becomes shallower. So if the MCP is the same, that means they will have the same slope basically. So the same goes with the fine green. The same goes with the other one, the below pinch. So this is then the fix, yeah. This is then the hot stream. This is then cold streams. The same goes over here. So if the hot stream has the MCP small, if it has a small MCP, that means the slope will be steeper. It will become something like this. So this is not allowed. This is not allowed. So in this case, we have to have MCP here. MCP of the hot stream has to be bigger. So MCP hot has to be bigger than MCP cold. In this case, yeah, below pinch. And above pinch, MCP cold has to be larger or equal to MCP hot, and then below pinch, hot has to be larger or equal to the C. So that is then the explanation of this guy. Yeah, you don't need to memorize this. It's just you need to know why it has to be that way. So we start doing from the most constrained point, means we then see which one can we manage, can we mix, sorry, can we match. Say for example, yeah, above pinch is over here, it's in the above pinch, this is then below pinch. So above pinch is we need to find C larger than H. So C is then this one, so it has to be matched with the one larger. So this is 3, this is 2, so they cannot be matched, but this one can be matched with this guy. So we can have this. This one can be matched with that guy, so we can also have this one. Very simple. And then the other one is also H has to be larger than C. So this is then H, and then this is H, C. It has to be larger than the C. The only one larger than this, this is the biggest one, so there's nothing else. This one is smallest one, so we cannot do anything. So this one, the only thing that larger than this one. So we can then have this is then one connection over there. So this is basically the connections that we can do. How much? That's something that you can calculate yourself. Yeah. The most important thing is then we need to maximize the heat recovery, so we can have as much as possible, and then we can then calculate how much then the outlet temperature corresponds to that particular heat exchanger. So this is what I did. What we have. So we start at this. So you can see here. So it's the same. So this one, that one, the other one. So we have this, and then calculate the duty. You can calculate also the duty, calculate the outlet temperature, and then the rest, for example, we can then yeah, this one is the additional one. So this is then the rest that we can do as much as possible, and then we can then get the heater over here 15 kilowatts, and then the cooler over there 105 kilowatts. So this 105 kilowatt and 15 kilowatt is exactly the same as what we foresee in the targeting phase. So that's how we design this. Basically, yeah, without going into too much detail, I think I give you already some hints on what to do and how to do that, but not in detail. And then I'm now waiting for your questions before I stop my presentations over here. So once we get this final design, and then this is what we could do. Yeah, we could do either in your design project or later on in practice. We can have our base case design, and then we have options 1, for example. We have option 1, and then we have option 2 and 3 and 4 and so on and so forth. So we can, from this base case design, we know how much then the hot utility, cold utility. You can also quickly calculate the investment required. The same goes with the design number 1, for example. Yeah? For example, design number 1, I just want to have like one exchanger or two process-to-process heat exchangers, and then I can calculate how much is then the hot utility, cold utility, and then the required investment, and so on and so forth with the other options as well. So from here, you can then, for example, you can then calculate, for example, total cost, for example, total cost. Yeah, all this costing you need to find in the textbook, like Tauler and Sinot. I think chemical engineering design or something. That's the name of the book. It has these cost functions, and then from here, you can then see, for example, this is A, this is B, and then this is C, for example, and then B is then the smallest one. So you pick then design 1, for example. Yeah. For example, pick design 1, and then, for example, and then you can then from here, this is then the base case, this is then your base case, and this then your, you can still remember this, and this then your the best. Yeah, this is base case, this is best case. So you can have this. So this then the this is then the heating, the cooling utility, this is the hot utility, and so on and so forth. So we can you can then have this side by side and then present it to your supervisor or examiners and see. So this is what we have come up with. So this is then our base case design, and then this is then our optimum design or better design or whatnot, design number 1, for example. Yeah. It comes with this capex, for example, this opex, for example, and then we have this total cost, and this total cost is lower than this total cost. So this is typically the journey that we do. The same goes with us here on the field. In your case, you have to present this to your supervisors or examiners or reviewers or whatnot. In our case, we present this to our management so that we can get money. Yeah, simple. So we can get money. They give us money to build this with the capex, and then we can then have this installed, and then we can then tell a story. Okay, how this design is then better than the base case design or other designs that we can think of, because it will then reduce the energy requirement, it will then reduce the CO2 equivalent emission, blah blah blah, and blah blah blah, and etc. etc. So the take-home messages is that be very careful with your data, because in some cases your data is not there or whatnot, or maybe it doesn't make sense. Yeah, it's also a place for you to check your simulation as well, because if you put like if you have like a wrong input or whatnot, you may end up with the illogical data or numbers. So be careful with that, and then you have to understand your process inside out. That's very important. What you can modify, what you can add, what you can remove, etc., etc., and then do the modifications if it benefits you. Because we could do many modifications, but see if that you can then always come back to that composite curve or grand composite curve. Yeah, because we have the software to do so. We can do it very quickly. So you do some modifications, you check the composite curve, for example, like this, and then you do another modifications, you check the composite curve, and then becomes like that. So it's not a good modifications. So I will stick with this one, for example. And then it's always, just explore several possibilities so that you can compare yourself and evaluate it very quickly. And then from that, you can people can then see what you have done. Yeah, I have this base case, this option 1, option 2, etc., etc. And then based on these 3 or 4 options, this option number 3 or number 4 is then the best one. So hence I picked that one. So by building up such a story, doing this work and building up such a story, people can then realize the magnitude of the problem. They can then see how hardworking you are, and then they also see that this is the best option that we can think of. I mean, we have done our extra work to explore possibilities, and this is basically what we can think of, yeah, given this team, given these resources and the time constraint. So I will stop my presentations with this. Do you have any questions? I think please ask questions. Yeah. Please ask questions.
This pinch technology also can be applied for offshore production facilities, right?
Yeah, it can be applied for anything that requires heating and cooling.
Then, yeah, as I can see, we have before pinch and after pinch, right? So, in terms of space or pipe routing, okay, as I can see, because before and after the routing is different. Is it we need to consider on the space? Can you advise?
Yeah. In practice, yes. In practice, yes. But in design project undergraduate, I wouldn't think so, because you don't have to. But in practice, yes. In practice, yes. Say for example, yeah. These are our existing systems.
Like brownfield modification, for instance, for brownfield offshore modification, maybe, for instance.
Yeah, we have to think about the space. Yeah, we can, because we say we add one exchanger over here, we add one over there, so we have now 2 exchanges extra, for example. Yeah, so is there a space that we can put these exchanges? So we have to think on that. That's why we need to have this mechanical and operation team in the team, operation people in the team. Sorry. And then it's also that's number 1, and then number 2 as well, because we are now having a different routes, yeah. So we need to be careful on the hydraulics. Can it still flow? If it cannot flow, that means we have to change the pump as well. So now I have now this stream instead of one exchanger, and now it goes to 2 exchanges. So this pump, can it get this 2 exchanger pressure drop or not? And if it takes a different route, I mean it's a longer route, can that get as well for the pressure drop for that longer route? So from that perspective, we have to check that. But in the field, we have different stages of projects. This one, basically, we do these options elaborations. We do typically during what we call FEL1 or FEL2, I don't remember, like conceptual design, yeah. And then this is then approved, because in this conceptual design, for example, we have say for example 3 options. So we have 1, 2, 3 options. And then we can say, option 1 is then the best one. So in the next phase of the project, we only evaluate option 1. Yeah, only means quote and then option 1 and then quote. So only option 1, and then the next phase we do these hydraulic calculations. We check about the space availability. If it's sufficient, so if it's okay, we can then move on for the EPC project, so the engineering project for this option 1. If it's not, maybe we have to have a fallback scenario. We can then have option 2, for example, option 2. Maybe it's not that different from option 1. It's just slightly worse, but then it doesn't need to have more space. Maybe it needs just to have a small impeller change or whatnot. So if this is more feasible in practice, even though it is more expensive than this one, yes, we can then opt for this as well as a fallback scenario. So all of these practical approaches we can then divide them into different phases of the project.
Okay, thank you, Tupan.
Yeah. Any more? For example, yeah.
What PTS number are you referring? PTS. Is that
that one PTS? No, there's no PTS for heat integration.
okay. Thank you.
but there is no need for having standard. Yeah, this standardization is only for how to design the exchanger, for example, and then on how to do the hydraulic calculations. But which exchanger, which process to process stream that we can then connect, it's just it depends on our creativity, depends on our understanding on the process. So once we know this process can be exchanged with the other process, we know, right? And then this is then the profitable options. Then we can then go back to the standard. Okay, so how do we design this exchanger properly? That's where we need to have the standard. But then having that connections visible, there is no standard for that. This one is then the Excel spreadsheet that I mentioned. If you go this one, yeah, the Excel spreadsheet for this guy. Can I open this? Just to give you hey, come on, just to give you and then you could also like hints, give configuration. So it comes from this paper from Spain. I'm not really sure if we have the I think this one, yeah. I'm not really sure. I have it. I mean, I have this software in my drive. I can then share it with you later on. I'm not really sure if it's hint somewhere here. Oh, this is my slides. Hint. This okay. I don't know. In any case, I will share with you what that software later. But this is then the iChemie software. Yeah, this is then the iChemie software that comes from that book of Chem. We can then have the yeah, you can read this, but then I will just show you. So we have this input, so we can say the name of the streams and then supply temperature, required temperature, delta T min that you would want to have. So if you say you can also put this by default, yeah, and then you can just use this. I think you can, so for example, use this. So if we delete them, it will then go by default. And then we have this heat capacity that we have to key in. Yeah, all of this. If it's white, that means we have to key it in, and then all these grays, it will be calculated accordingly. So you can see the heat flow is then being calculated, and it will then automatically identify it's hot or cold streams. And then it also uses from this delta T min that we apply, it uses this shifted temperature. If it's cold, if it's hot stream, that means it has to be reduced by half. If it's cold stream, it has to be increased by half, for example, yeah. So 19 plus 2.5 is then 25.5, 21.5, 20 plus half plus 2.5, 22.5 or something like that. So if I keep it, and then I will then use this number. So for example, this 19, you use this 2.5, right? And then how do you call it? Coincidentally, it's the same, yeah. It's a 2.5 for the cold, 2.5 for the hot. So we can still the same number. So from here, we can it will do the problem cascade algorithm automatically, identifies for us the pinch point, which is then happens to be in the minus 21.5 degrees C. And then the hot pinch temperature, cold pinch temperature, and 21.5 is somewhere in between. And it has this hot and cold utility. How do you call it? Coincidentally, it has this. They have the same value. And then we can see the cold composite curve is the composite curve like this. So this is then the area where the heat can be external heat. This is then the external heat to discharge. This is then the area where we have to recover some heat. We can also have this is then we still see some distance, yeah. This is then the actual, because they use the actual temperature. If they use this shifted temperature, there is no distance anymore. So this is then the pinch point. Pinch point is, which is then minus 21.5. So we can see the grid diagram is over here. So we can quickly see. So having this and that, and also obviously we need to have the numbers. Yeah, this is enough for our first point to investigate what are the options to recover heat. This one is the grid diagram. If you want to, we cannot design the heat exchanger automatically, so we have to design it manually, like I showed before for this heat exchanger network. And the rest is not so much important. This delta T min as well, we can then see. Say for example, using this data, it has this delta T of 5 degrees C. I don't know if I do this, because if I do this, it won't be using that number. So I have to remove this, and then it will be using this number. And then I can then run the cases by varying this number. That's what it means. So I can then vary. Minimum is then maybe, I don't know, maybe 2 degrees C, because now it's 5. Maximum is then 20, for example. Yeah, and then I can just quick run cases. Hopefully it works. Does it work? Doesn't work. Anyhow, I have one Excel sheet that works. I don't know what happens with this one, but in any case, I will share with you the version of mine that this macro works. Yeah, because this is XLS. We have to XLSM against the macro. In any case, at least this gives us like a simple tool. Once we make our flow sheets, we identify the streams, we can put the streams in it, then we can know what is then the minimum utility, how it looks like, where we can then place the utility system, so to say. So we can then change this to 10, for example. This one will change. That one was changed. It was 1840, right? This one will change as well. See, this one hopefully change. Yeah, it will change. So the pinch temperature shifted from here to there, and gives then the whole different platform. I mean, the different utility systems and different heat exchanger design later on. Any more questions? Anything? Please, you have to ask me. I've shown you this. I don't have this one, so I don't know, because I cannot show you that one. This one I have it, but I don't think we have time to go through this at this point in time. Anything that is related to that. This project, for example. What we did is that you have can you see there's a pointer. So can you see this numbering? This is number 1. See this number 1. Can I zoom in? For example, so this is then our options. Option 1, this is option 2, option 3A, option 4, 5, and so on until option 8. So we have different options. So in the end, I think we have we can also make a combination of option 1 plus option 2 and so on and so forth. So we have dozens of options in the end, where we can then calculate the cost functions. So in the end, we could generate dozens of these tables, and then we can then say to them, okay, we have our base case designs, and then for a little bit of investment, for example, option 1, maybe, so we can therefore have improvement of this number. So if we want to pay a little bit more for the capex, we have another improvement, and so on and so forth. So then the management or anybody whom you are going to present this, they will then say, okay, so this is then our ground work, and then if we pay some more, we'll have disadvantages, and a little bit more, we have disadvantages. So we don't then put them all in once, and we present to them stage-wise of improvement. So this works perfectly in practice, but in your case, you could do so as well. In the undergraduate design, you could do so as well. You can then have different options, or you can then just dump them all of, just do the complete change of the heat exchanger network and then present it as like option 1, the complete one, and then the next option is then a completely different option. For example, yeah, you could do so. So whatever you need to do, you think you have to do, as long as it is clear for the people outside there, they can see the improvement from your base case, option 1, option 2, and option 3. We typically happy. Yeah. Any other questions? Maybe I'm speaking too fast here. I don't know. Maybe it's not very clear. Students, any questions? Is it clear or is it helpful? How helpful? Yeah, I'm not going to ask. Is it helpful? So how helpful is this session so far? 1 hour 29 minutes. Is it something that you can apply, or you have applied this already? This design project, they are in the almost completing or just about to start? So where are they? Where are you guys?
They just start this semester. This is their design project 1. Now it's week 7.
Okay. So they are now in which phase? I mean, they have the flow sheet already or not yet?
Basically, based on my group, they just started to develop all the process.
Oh, okay.
The process.
Okay,
so I think they are yet to think about the process integration.
Oh, okay. But they have this heat integration course before, yeah, and like before this project.
We have one course, renewable and sustainable energy engineering. So we embed the concept of process integration in that course. So basically, all of them already have a little bit exposure on process integration.
But that course is not heat integration because I mean, this heat integration must be like a smaller parts.
Yes.
Okay. So it's going to be difficult, yeah. So you guys need to open some textbooks again and then do some more exercises. By the way, this design project will then help you. I mean, it's all learning by doing, because we are not going to be experts in this by only watching YouTube videos or listening to me speaking. So you have to really do it, and then really do it, and then you know how difficult that is.
During in renewable and energy engineering, they just expose so meaning that for design project they have the real case. However, Dr. Zufan, I have one question.
Okay, you can have 10 questions.
But if the student need to do the optimizations for the process for the heat integrations, so to what extent they need to prove the optimization step for the process integration? So is it just by comparing the base case, improve design 1 and improve design 2 that this can be considered as optimizations, or what's your opinion on this?
On that. Okay, it's very good. Yeah, next question is also very relevant. If we are in an optimization group, like in the group of Professor Grossman and Carnegie Mellon universities, they will ask you to do a kind of like a mathematical optimizations, which you have to do, otherwise you won't graduate. That's one. But in real life, are we going to do that? Obviously, no. In real life, the tools that they develop, we can use them. What we do, I think it's also in our design project and also in a real life design, what we do is we have to have a base case. I normally use this silly example on finding the highest mountain in the world, yeah, which is the Mount Everest. We know them, but then how do we know if the Mount Everest is the highest mountain? How do we know that? We know that because we have seen the other mountains, right? We have options. So those other mountains are the options. We know how high is the Kinabalu mountain. Yeah, the Mount Kinabalu. We know how high that is, and then we know how high is the Kilimanjaro, for example. or the Andes Mountains in the South American, and then we know also the height of the Mount Everest. So we have now Mount Kinabalu, Mount Andes, and then Mount Kilimanjaro, and then Mount Everest. We have 4 options. And then in these 4 options, we know, okay, these are that amount of thousands of meters, that thousands of meters, and then we have the Mount Everest 8,800 meters. So by comparing these options, which we know, and then we can safely say this Mount Everest is then the highest one. The same goes with the design, like the Rainer mentions very rightly. So we have option 1, option 2, option 3, option 4, or design 1, design 2, design 3, design 4, from which we can compare. Yeah, we know what is then the capex for each of these options. We know what is then the opex of these options. And then we know what is then, for example, the total cost or the total profit or whatnot. And then we can use these parameters to as a comparison basis. So for example, if we want to have options with the lowest capex, you can simply compare the capex. So capex 1, capex 2, capex 3, capex 4, which one has the lowest capex? Maybe capex 4. So this design 4 could be then one option, or we can say that this is then the minimum options. But if we think about it globally, because typically for one design, it needs more capex, but it will then save in the long run. In the long run for the opex, we can then use profit, for example. So in this profit, we take into account how expensive and how much is then the capacity of the plant, how much money do we need to build the plant, how much we have to pay for operating the plant. So in that sense, we use profits as the benchmark. So we have profit 1, profit 2, profit 3, profit 4, and then we can see maybe profit 2. Yeah, design number 2 gives profit 2. This is then the highest profit. So we can then safely say out of these 4 options, this profit number 2 is then the best design. We could do so. Yeah, we could do so. Another approach is then to combine this mathematical optimization and then with this practical approach. How to do so is that this one a little bit tricky. We have our flow sheet. Yeah, we have our flow sheets. And then in this flow sheet, we may or may not know. Yeah, I mean, do I have to run this reflux by 1 or 1.5 or 2? Or shall I make the split factor this and that? Or shall I increase the conventions? If I increase the conventions, the selectivity will drop, and so on and so forth. So we could use this reflux ratio, we could use the split factor, you could use also the conventions as our handling. So we need to know how much what is then the values of these 3 variables in such a way that the flow sheet will then give me the highest profit. Yeah, we could use that. So in this flow sheets, I think in all process simulation software like ISYS, Symmetry, Pro2, what else? Yeah, they have options on optimization toolbox. So we can use this optimization toolbox, and then we can then utilize it to find the so to say the best operating point, for example. Yeah, and then we can then have this as the 5th options, or I don't know, option A.1 or 1.1 or something. So we can do so as well. See if it converges. If it's not, and then we have to do it manually. We have to change the value manually and see how much is then the profit. Otherwise, the practical approach is also fine. Optimization is another class. Yeah, it's another course. I think the most important one is that how do we know that we are better or we have something better? The one requirement is that we have to have a competitor, and then we have to be able to evaluate the competitor with us, and then we can then show that we are better. So that's basically in a nutshell, how optimization really works. So I don't know, does that make sense? So if not, then you can ask me more. So more questions. I think I need to have questions from the students. 28, 20, 21, 22, 24. This is all in one batch, yeah. Because in UTP we have, I think, 2 batches overlapping in one course typically.
Most of them are final year student.
I mean, it's also in UTP. So we have final, and we have a term final, and then final first. what I don't know. So because the semesters are overlapping, so we have the senior final and then junior final. They may take the same course together. I don't know about UniKL. Are they all coming from the same batch?
Most of them, because UTP they have 3 semester in 1 year. We only have 2.
Okay.
2 semester.
Okay. Please, more questions. No question. No. Yeah, when we just started, when you start, this is the very best. I mean, it's one of the best books to start for students. Yeah, I would say. It teaches us on conceptually how to design, what to design, and how to design them. So it helps a lot. At least for me, it helps a lot in making sense of what we have been learning for 4 years of undergraduate studies. So I read this book in my postgraduate studies. So it started to make sense for me. Why we learn reactors, chemical, whatnot, distillation columns, how to design them. So any questions? No questions. They're very shy. Yeah, are they very shy? When in UTP, I would expect I would get like at least 1, 2, 3, 4 questions. Not a lot, but then some questions are there. But yeah.
Hi, sir.
Yeah. Please.
Okay. So I want to ask a question. So before this, you mentioned that to do the software called HINT, right? HINT.
Can you find it?
Okay. So that means most of the company use that software to do the calculation and so on.
No. That software, as you see, I think you need to experience it yourself. It's a bit difficult to because if we make one mistake, we have to redo. Yeah, if not really sure. It's a bit cumbersome. It's a bit cumbersome. That's okay. So it's good. It's good for teaching and learning, because that was the intention of that HINT software. Good for teaching and learning, but for commercially, people either use super targets or Aspen Exchange Analyzer. Here in Petronas, we don't have super targets, so we make use of super target, or we design it manually. Like in all of my projects, I design it manually, because it's the same. I mean, the workflow is the same. Like I've told you, the same workflow, and then with a reasonable amount of streams, to handle, so we can have we are in full control on the design of the heat exchanger network, and then it's also not that big, so we can handle it well. So within the time frame of the project, having Excel and then manual design, it's sufficient. But do you have? I mean, can you find this HINT software in online?
I just did the research, but for now, I don't find yet. But there's another software called Pro P1 something. Maybe that one, that was the alternative software for heat integration.
Oh. For what? Maybe I need to, because I need to learn from you, yeah. For what?
Pro PI1. Yes.
PI1.
Yeah.
Oh.
I just Google PI1 software.
PI1, like this. One. PI. Lenovo. I don't know. PI.
Pro PI1 something. It is a computer software.
Oh.
But I think that. No.
Okay, I don't know this. Thank you. Oh, this one. Oh, this is the hint. So you can then see this in zip form. So you can install this, and then this one copy. I don't know this one. So thank you for this. So maybe I can then try this. Very good. This photo. This is the guy. I think the IEA, International Energy Agency. This guy wrote the energy heat integration primer something. So I think he gives this table on typical delta T. Yeah? I think, yeah. I'm not really quite sure, but I think I saw his name somewhere. Oh, interesting. The figure, no figure. Thank you. So I can use this as well, right? So this is this looking back here, if I may, this heat integration skill or pinch analysis skill, it has been around since early 80s or late 70s, but because we typically teach this in the final year of the conventional chemical engineering curriculum, so we don't put like too much effort or emphasis on applying this to get more practice in this course, for example. It happens in UTP as well. I mean, we get this. Yes, we have like one semester to teach this course, and then we implement this in our design project. But again, this is a skill, yeah. Skill. It needs to be practiced. So because of this, it's at the final year, and then not all universities are teaching this. So even though it already like 80, 90, 20, so it's more than, or even more than 40 years already. Not so many, also only like a handful engineers can do this. Yeah, only a handful of engineers can do this. So I'm telling you that if you are good at this, or if you have passions in this design, and then you go for it, and then people will look for you, because we need to be like more and more environmentally friendly, and this pinch analysis is one of the techniques to get to that situation, more environmentally friendly plants. Any questions? We don't have questions in the chat. Yeah, if you are too shy, you can just write questions in the chat. So that's what we do as well. But just like Shawalni. So very brave. Thank you. More questions?
That's so fun. How many streams that you have when you design, when you do the process, the pinch analysis? How many streams that you have when you do it manually? Because normally last time I also teach process integration. Normally students have minimum 4, so maybe the highest, the maximum number is like 8 to 10. So in the industry, so when you do it manually, how many streams that you have? I think it's quite time consuming.
This is time consuming, but since I've done this many times, so it's not that time consuming anymore. But at least making the first hurdle. It is then the most. This is the most. This is the one with the most streams. This chemical plant is only like 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 streams in total. This one's also not that many. I mean, it's around 20 something streams, but this one I think it goes to 1, 2, 3, 4, 5. And it's quite many. Let's say I think I counted once. It's about more than 30 streams. And this one I develop. The most difficult one is then to get the data right. So once we get the data right, I draw it in like a PowerPoint. So it took me like at least a day or 2 days, to make to check it again, see if the data is correct, because we can make mistakes. So that's the use of the software. But in this case, I'll tell you later why I don't use software. So in this case, I make sure that all the data is correct, in and out flow and stuff, and then how the existing configurations are located. So I think I spent 2 days on this, getting the base case ready. So once we get the base case ready, it's the 2 days, and then we can then explore the improvements. So these improvements we can yeah, we can have another 2 days to improve to find some improvements not in rushing. Yeah, so we have to do it in a relaxed mode. And then at least maybe 1 week to get the base case, as well as to get some options ready. Yeah, 1 week I think is quite time. At least that is then the amount of time that we need to have that I have spent, especially on this project. Yeah, why I don't use software? Number one, in this particular case, I will make it yeah. In this particular case, as my why I don't use software, especially because we can use Aspen Energy Analyzer. Yeah, so this Aspen Energy Analyzer, number one, is not very like user friendly, so I cannot navigate from right to left, up down very easily. It's not very flexible. It's not very flexible. That's number one, and then the biggest one. And then the second one is that typically when we put all the when we put all the data into the tables that they provide, they will then typically assign all of this. The top is then the hot streams, and then the bottom part is then the cold streams. In this particular case, I don't want to do this because we have two complex, right? The CFU and then the CDU. So we have hot streams on the CFU and cold streams on the CF2. Also, hot stream on the CDU and then cold streams on the CDU. So what I do is that this part, then the CDU part, and then this is then the CFU part. So if you use software, at least this Aspen Energy Analyzer, we will not be able to separate them because by default, all hot streams in the top, all cold streams in the bottom. Why I need to separate them? Because I have two complex, and then I need to maximize the heat recovery from one complex first. Now, once I know that we can then maximize them, and then maximize this and then maximize that, and then if there is a need for that, we can then see is there any heats that we can then transfer between these two complex, which is in this case option number 8. Option number 8 is then one heat is then being transferred from one complex to the other. But this is option number 8, and then we know, yeah, because this complex is very far away from each other. So having these segregations, it helps a lot in terms of having the practicality in advance. Because I know in option 1 and option 7, they are much more cheaper compared to option 8. Because option 8, we need to install pumps as well, because they are very far. So these two are the reasons that why we did not use software at the time. But we could use software if depending on the case as well.
That's impressive. Thank you, Dr. Zulfan.
Dr. Zulfan, I have a question.
Please.
Can you please show example of economic analysis from your base case design to your best case design in terms of the energy cost and the capital cost?
I don't have that example. I mean, I intentionally don't use any numbers. But in this case, like in this case, I have 8 options, right? I have 8 options, and I have also combinations of options. So I have options 1 and 3, and then in the end, in this case, yeah, I have options 1, option 1, option 3, option 5, option 8 in this. So we have initially 8 options, and then we kill some of them. So we were left with option 1, 3, 5, and 8. So that is 4 options as a base. And then we have several other options as a combination. So we have option 1 and 3, option 1, 3, 5, and then 1, 3, 5, 8. So we have 1, 3, 5, 8, and then 1 and 3, and then 1, 3, 5, and then 1, 3, 5, 8. So in the end, we have 7 options. So these 7 options is what we put in this table. Where's my table? Sorry. So this option. So I have 8. I have 8. So I have 8, 1 until 8. options over here. So in that options, we have our capex, and then we have our CO2 emissions, and we have our we have also the opex. Yeah, we have opex, and then we have the total cost, and then saving. Sorry, why is this so ugly? Yeah? Saving, sorry. Savings, total cost. So we make tables like this. This utilities is not really important because they don't want to see this. Yeah, we need to know money and CO2 emissions. So we have our investments data, we have our OPEX data, we have our total cost data, we have savings data. This one is in terms of megawatts. And then we have the CO2 equivalent emissions in terms of kilogram per hour. So we have all of these numbers, and where we can use them as a comparison. But the actual numbers, yeah, I mean, I don't put them, and I don't think it's wise to put them here. It's just like so that sharing the how I did that is sufficient. Sorry for that.
Thank you.
More questions?
Doctor, I have a question.
Yes, please.
During when we do the pinch analysis, if we have like we have lack of data in some unit, what should we do to have to overcome that?
Yeah, excellent. If we have lack of data, I mean, in your case, it's not. I mean, it's very rare to have lack of data, yeah, for doing this, yeah, because we do this after we have the where was it? My onion diagram. Okay, this one. Okay. So we do this only after we design the reactor, and then we have the separation and recycle system. So basically, we have this kind of flow sheets. So we have this kind of flow sheets where we calculate a mass and energy balance using software. Typically, yeah, you can use HYSYS or O2 or Aspen Plus or Symmetry. So you can use those software to make this mass and energy balance, and then you will know then the requirement for heating and cooling. Now, once we know the requirement for heating and cooling, we get that data, and then we do what we just did. In practice, we don't have such luxury because, like I said, in some streams, we don't have any flow measurements. We don't have any flow measurements. We may not have any temperature measurements. So for that, we go back to the design case, and then we try to make a simulation using the design case. See if we can then match the design, and then we can then change the inputs in such a way that we can try to mimic the current operations. Yeah, so we have a simulation, simulations on the design mass balance, and then that's number one, and then number two is then we simulate operational data. Yeah, and then number three is then to extract the data. So number three is then extract. Why is this so not so good? Number three, extract the data. So once we get our simulation model closely matching the current situations, yeah, and then we can use the results as the data source. So for example, if we don't have the temperature measurements over here, so by using the simulation data, we can then use the temperature calculated over here as the outlet temperature. So this one now we can then use it in our further heat integration study in this case. So that's what we did. Does it answer your questions? Was it Sufyan? Yeah. Does it answer your question, Sufyan?
Yes, doctor. Thank you, doctor.
Any more questions? More question? No more question. In design, yeah, I know, yeah. In design, not only you, not only you, even the engineers who have no experience in design. I mean, like a typical engineers, we don't design plans. We just follow whatever the licensors say. But in design project nowadays, you are acting like a licensor of the technology. So you are the Shell, the ExxonMobil, the DSM. So all of those big companies with big R&Ds where they create processes. I don't know where was I going with this, but in any case, so so there are lots of uncertainties. Because we are starting from scratch. For example, like in your case, you're starting from scratch. There are some with no data, right? So, I mean, you may or may not have like a kinetics. You may or may not have like conversion data. So for that, we need to read literature. We need to go back to experiments. We need to do our labs. So that's what we do, yeah, these licenses. We need to go to their labs. They need to work together, the chemists and then the chemical engineers. They need to go like a back and forth. So this is basically what we have seen in the classroom. It seems like a one-way route, right? It seems like a one-way route. So once we design this, we go there, and then we go here, and then we go there, and then we go there. So in practice, this is not one-way route. This is not jalan sahala. This is back and forth discussions. Yeah, this is back and forth discussions. Because what we think we know in this phase, it may not be the case when we go to this phase. So the more we go in the project. So we have R&D, we have feasibility study, we have conceptual design, we have EPCC engineering, and then we have our plans. So it's all back and forth discussions. So it goes there, it goes come back here, it goes there, it comes back here. At least until this feasibility and then conceptual design. These are what is happening in this onion diagram. So they go back and forth, back and forth, back and forth. Because one route, for example, we make one route and then it dies because of not economic. The other route it dies because it's not technologically advanced, or we need some more advanced technology. So we have plenty of options. And then from these options, you can then generate several alternatives. And then from one of these alternatives, it can go moving forward from the conceptual to the EPC. So in this case, yes, it goes straight. It goes jalan sahala. Yeah. But from here, there it goes back and forth, back and forth, back and forth, back and forth until you are left like a board. So how to do this back and forth, back and forth? Ask seniors, go to the lab, read literature review, read patterns, and then discuss with your supervisors in this case, yeah, because we discuss with our supervisors, we discuss with our boss, we discuss with experts. So it's there's no harm, yeah, there's no harm to make mistakes, because indeed this is then the place that where you can make mistakes, especially in the R&D. Once you go here, there is no more mistake allowed, because it costs a lot more money. So in this case, yeah, make one route, it's not working, the other route's not working, the other route not economic, the other route not technically feasible, and so on and so forth. So by the end of this exercise, that's why this R&D takes like 5, 7, 10 years even. So depending on the complexity of the technologies. So you have to discuss, yeah. We don't know a lot. So that means we have to talk to people. We have to ask questions. We have to know what we want. Yeah, for example, I want to design a reactor. So what information do I need? So you may forget already what you need to do, what you have done in reaction engineering class, right? So it happens if we don't know. Okay, so to design a reactor, what do I need? So I need to know the chemistry. I need to know the chemical properties. I need to know the safety informations. So you go back to that class. You go back to your lecture notes. You go back to your reaction engineering lecturer even, and then ask or discuss what are things that what you think you should be doing, and then ask them for their opinion. Yeah, it's not that you go to the supervisors or you go to the lecturers, you go blank. Yeah, it's not allowed. It's not professional at all. Yeah, you you do your homework, make your preparations, and then you present to them. This is what I think it is. This is what I think that I should be doing. So what do you think, please? So that's how you approach your colleagues or your superiors or your boss or your experts or your lecturers. Yeah, you don't go, sir, I don't know this. Can you teach me? No. It's not. That is not a good way, and that is not a professional way to do. Yeah, do your homework first. Make your presentations, make yourself clear, and then present it, and then share it, and then discuss it. That's the only way. I think I've spoken too much. Any more questions?
Any more question from the floor? I think if no more question from the floor, we can end the session, Dr. Zulfan. Is it okay?
Fine.
Anything from you?
No, I mean, well, you can always ask me. You can always ask me. We can always have discussions. I like to share what I know. Like I said, you are the future engineers that this country has, or maybe the world has. So everything that we have done in the past, you have to be able to continue that, and then you have to make it better. So to make it better, you have to have our knowledge and then advance that knowledge. So to do that, we have to keep on learning, and new technologies come in. Like nowadays, we have now AI, machine learning, data analytics, and stuff. So these courses are also not typically taught in conventional chemical engineering curriculum, but I'm assuring you that they will come in the future because we need them. We need people with chemical engineering background. They need to be able to do design, do simulations, do optimizations, do data analytics, very proficient in programming. We need these people in the future. So this is what we call as process engineer of the future. But take a step, take a small step, keep on learning, and then you will get there. Yeah, it sounds very overwhelming, but it's not. Trust me, it's not. So you just have to learn a little bit, like spend half an hour, 1 hour per day extra, and then after 1 year, you realize by then you will realize how much you have accomplished. Yeah, so I wish you all good luck. If you have any questions, I'm always free. We can always discuss. Yeah, but please don't. Not everybody ask me questions. So I'm always okay to share my knowledge. Thank you. Wish you all the best luck in your design project and your career.